seeing if this works. All right, I think this is working. Okay, cool. All right, hey everybody. All right, I haven't done a live stream in ages. The kids have only just come back to school, so I've finally got the opportunity to do this. And I've been playing with some stuff the last week, and I wanted to kind of share what I've been doing and talk about it a bit because it's like really in the news now. Not what I've been doing, but this whole idea in general. And I guess the hype is around these reasoning models and in particular DeepSeek for a whole number of reasons. But the DeepSeek one, I think, is the one that's caught everyone's attention is R1, which is a reasoning model. And it's caught people's attention because it's available for free. You can download it. You can run it on your local machine in something like Llama. It's similar to Quen, which I did a post about probably about a month ago now. So it's kind of similar in terms of the way it thinks and the way it reasons. And what I'm really interested in with these particular models is that they can do some more complicated sort of thought process. And in particular, I'm really interested in performance. So like I'm interested in trying to do optimizations on projects and thinking about like what code optimizations you can do. So I've been tinkering, not just with R1, but with Llama 3.3 70B Instruct as well, and also trying to use O1, which is OpenAI's reasoning model. I mentioned before that these types of models are a bit different to maybe what you've used already. So this is the code I'm going to be looking at. This is CPython. It's the Python source code, so like the source code for Python itself. And what I wanted to do was to essentially try and optimize some of this code and explore in more detail, like whether it could be faster, and if so, like how would it work? And it's not straightforward. It's a really hard problem to work on. And if I give this problem to like a model that you might see like today, like GPT-4o, for example, if I just bring up a new chat window, if I say I'm working on this function and I say, can you make this more efficient? Then GPT-4o is going to make general suggestions based on like patterns that it knows, algorithms that it understands. And it says we can try and minimize the number of operations inside the loop. One way is to reduce the number of bitwise operations and conditional checks. Here's a revised version of the function. I should probably explain what this function does actually. So inside CPython, we've got different types, and one of those types is the number type. So they're like integers. Integers are not like they are in some other languages in Python. They're actually arrays of digits. So that's how we can do like really big calculations in Python. So if I'm, I can do, I don't know, like ridiculous calculations like this. Take out the U. And yeah, that's way beyond a 64-bit integer, like the size of it. And it works because essentially it stores pieces of information in an array inside Python. So when it does multiplications, it doesn't do the instructions on the CPU like it would with some languages like C++. It essentially has to do like vector arithmetic to do multiplications and additions and stuff like that, which makes it really flexible because you can work with huge numbers, but it also makes it a little bit slower in some cases. So deep within the source code of Python is all these different algorithms, and they essentially do like the subtraction, addition, exponents. You can do like left shift, for example. So like all of that implementation has to be customized because it's working on arrays instead of just like simple 64-bit integers. So if I gave, actually let's not undo that because that's jumping ahead a bit. Okay, cool. That's the original function for doing an in-place add, and this is the function I wanted to test with these models. And if I asked GPT-4o, it's going to kind of give a general recommendation on that function, which is like, can you reduce the bitwise operations? Here's a revised version. I'm looking at that and can't see any way that would be different without changing the behavior. It's saying it's reduced the number of operations inside the loops, but I can't see how that would work. We could try it, maybe it might work, I don't know. Let's give it a go, it's fun. So yeah, if we just copy and paste that into the code, YOLO, why not? Just give it a go. Then if I recompile Python, and it takes a second, but whilst it's doing that, so yeah, let's just see what happens. We had a lot of tests for this, so that's pretty cool. I've also turned on something which I'll talk about in a minute, which is on the compiler locally, I've turned on some extra flags. So I get this information about what the compiler is and isn't vectorizing. And I'll come back to that in a minute and the reasons why that's interesting to me. So I'm running on Mac OS. I've essentially changed the CPython source code. If you're not kind of familiar with this code base, most of it is in C. So what I've done is basically change the implementation for an in-place subtraction where the number that you're working on is big. So it's a large number. So if it works on small numbers, it actually just does normal like CPU instructions to do the arithmetic. But if it's a really big number, like the one I showed you before, it has to do like a vector. So in this function, digit is a pointer of size m to digits, and digits are the numbers inside the inside the integer array. They're base 2 to the power of 30 because it uses 30. It doesn't use base 10 in its digit storage, which is really confusing, and it makes it really hard for these AIs to like look at this code and guess what it's doing, because it thinks this is a subtraction and is guessing that you're doing it with base 10 numbers, but we're not. Okay, so we've compiled GPT-4o's suggestion, so we can test it out. We can run Python's like unit test suite. I don't want to run the whole thing because that would take too long. But there's a test module for long. So let's see, it passed. Okay. It's really hard to read and comprehend code whilst doing a live stream because I'm thinking about two things at once. So the math test pass. So GPT-4o has come up with a suggestion, and is that suggestion any faster? So all I've got is what we can do. What mode am I on? I'm just thinking. I was running CPython without debugging, which means that it uses like the full optimization. If I scroll up, I'll probably see the compile flags. If you see 03, okay, there we go. So that is a like C-Lang's optimization levels. If you're running in debug, it won't have any optimizations. If you're running in like a release mode, then you're building like a release binary, then it will. So at a glance, like it's changed that function. But if I go and look at the implementation, it's going to be quite hard to figure out what it's actually changed in the binary because the compiler itself has optimized it. So what we could do is, let's think, we could do a benchmark. I have not benchmarked that function yet though, so I can't think off the top of my head what the code would be, but the tests are passing, so that's interesting. Is it any faster? I'm going to come to the other one because I know how to test that one. This function is only used in certain cases, and you kind of need a repeatable test. So I'm going to ask it to optimize this one, and then we'll try that. Okay. Before we do that, we can run the benchmark for exponents, which is time it. The time it module, and you can give it a code snippet. And if I give it like do a big exponent, like I don't know, that's big enough. It will tell you how long that takes. Is it -C? No. Okay, so that takes 36 microseconds per loop. It's come up with basically the same suggestion. I think it's just move the code around. I don't think it's, and it's put some of the instructions on the same line, which in C like won't really make any difference because the C compiler is really smart. Like it hasn't really changed the algorithm, so I don't think that would make any difference. But we could try it. Why not? Okay. So I guess the challenge we've got here is that we can give these models effectively like a bit of context, and it can see the function, but we can't give it a whole list of rules and constraints that we want to work with. And when you're doing optimizations, you really want to explain like all the details of what it is you're trying to optimize. So in this case, what I'm actually trying to find is an implementation of this function that treats each operation, it can vectorize it. What that means in the actual code that gets executed on the CPU is there are special types of instructions on most modern CPUs, both Intel and ARM. These are like vectorized instructions, and essentially it can do like multiple calculations simultaneously. And because we kind of got up to 64-bit as being like the biggest you could do with numbers, if you're working with like big matrices of floating point numbers or integers, they add these specialized instructions so it can do sort of multiple calculations at once, which is awesome. But the conditions that the compiler needs in order to be able to compile in these like specialized instructions is pretty long, and it's pretty restrictive. And it's also not obvious to a programmer whether or not the compiler decide to like use these special instructions. You can kind of force it, so you can say like pragma clang loop vectorize enable like this. This is like an extra pragma statement that you put before the loop, and that will tell the compiler that the clang compiler that I really want that loop vectorized. And then when I run compile again, it's going to come up with a warning to say, I tried my hardest, but I really couldn't make it happen. Sorry about that. And give you some reasons why. Oh, it should do. I don't know why it didn't. Did I? Oh, I didn't save the file, that's why. That would help. Okay, so it should come up with a warning and say, yeah, that's not going to happen. I couldn't vectorize that loop because the transformation is disabled, because it's not supported, because of like the things inside the code. And this is kind of where I'm going with this live stream is, okay, that's what GPT-4o can do. It understands like general programming patterns, and it knows like the general rules of optimizing stuff, but it's done that based on all the code it's ever seen. And it's just going to apply those patterns. So it's just going to say, okay, this is like a before and after. and it will just like apply a general pattern. I can't provide it in my rules, or I could give it like a long list of instructions and rules in the context window. So the context window is the box, in this case, the chat box. But that's kind of like my instructions for GPT-4o. That's fairly limited. Like I could give it like 5 or 6 rules and it would kind of try its best to meet all of those rules. But it could come back with a suggestion that doesn't adhere to one of them, and it would just say, okay, here's my suggestion, here's my answer. Also, if it comes back with a suggestion which isn't faster and I tell it to make a better suggestion, it will kind of just recursively dig further into that suggestion. So what I wanted to do was to, let me undo my changes because I get to the thing I actually wanted to show you. So what I wanted to do was try a different type of model, and I wanted to give it the rules for CLang, so Clang, for Clang's compiler, so that instead of getting this warning saying we couldn't vectorize this loop because it doesn't meet the instructions, I wanted to give the AI the rules and say, here's the code, here's the rules, can you figure out a version of this code that meets the rules? And it should not change the behavior of what the code does. I think like a really experienced C engineer, especially one that does like these types of instructions, could probably figure this problem out. But I wanted to give this to an AI because it's fun and I don't know how to do it myself. And I also wanted to understand like how these models are different to what I've been doing currently in GPT-4o. And other classes of models which are like that. I can pick O1 in Copilot Chat now as well, which is like in the benchmarks is basically in line with DeepSeek R1. And you can give it a long list of instructions and rules, and it will try and come up with a solution that meets those. So that's kind of cool. The thing with O1 though, it doesn't tell you it's working out. So when I was testing this, it kind of said that's not possible. And what I wanted to see was like all of its thinking and its thought process. I haven't quite figured out why it was doing that. But I've got some other tools that we can use to like explore the different models. So one of these tools is GitHub Models, which is available for free. And what you can do in GitHub Models, you just sign into GitHub, go to marketplace/models, and then you can pick a model from the drop down. O1 is in there. DeepSeek R1 was added yesterday. And we've also got Llama 3.3, like the different sizes of the instruct model, which is a kind of similar type of model. And those are really the ones I wanted to play with. So I picked Llama 3.3 70B instruct first, because this is a model that has enhanced reasoning. Also the context window, so that's like the amount of information you can give it, is 128,000 tokens, which is big. The output window is quite small, so you couldn't get it to do like produce like a huge output. But in this case, I don't want a huge output. I just want it to give me a version of that function that meets the rules. And what I've done is basically taken the documentation for the auto vectorization algorithm in LLVM, and inside of there is like basically a description of what it does, how it works, what features it has, and then like how it handles unknown trip counts, like if it can't work out how many loops it's going to have, how it does reductions, if conversions, and which types of if conversions it supports and stuff like that. So this is a big document. What I could do is just like copy and paste that whole document into the AI and said, here's the documentation, can you read this? And then figure out whether or not the code meets what this is describing. But we're kind of asking it to do two things at once. We're asking it, first of all, to summarize this documentation and then turn it into a set of rules, and then go and apply that set of rules to this code. So with AIs like this, with LLMs, you kind of want to break things down into smaller steps so that you give it a step at a time. So what I did first is basically copied like the text in here, and then gave it the instruction to summarize this document as a set of rules that I would then give to another LLM. So LLMs turn out to be pretty good at writing instructions for themselves, which is pretty cool. So that's what I did, is copied and pasted the documentation, and I said, can you create a rule list for me? And I wrote this sort of preamble. This is on my Gist on GitHub. And I said, we gave it a job. So your job is to suggest optimizations in C by finding loops which could be vectorized. And I said, the Clang compiler has decided this loop cannot be vectorized. And I know that because I've seen it in the output, because it fails to meet one of the following rules. Your job is to work out which of these rules is not met in the code, then suggest an alternative block of code that would meet these requirements. The vectorizer will compile SIMD instructions, which is a single instruction, multiple dimensions, which is these special instructions that I was talking about, into the program. This is efficient when the instructions in the code are the same for each iteration, and they can be executed in parallel by multiple cores. So this is like my introduction to the problem that I want the AI to solve. And then this is the list of rules that it came up with. The top 3 I added because when I read what the AI produced from the documentation, it was kind of missing some of the really obvious ones, which is like the number of cycles in the loop has to be known when the loop starts. Otherwise it can't vectorize it. Like you can't have a while loop where the condition in the while statement can change through the cycles. Like it can't vectorize that because it doesn't know like how many cycles there are and how to split them up. So yeah, that's kind of me just kind of reinforcing that point and saying, okay, like here's the rule set based on LLVM's documentation. So that was its challenge. And I gave, we can do it now actually, let's just see what it does. I've been kicking these things for the last day and a half, and you do get rate limited. So I'm just copy and paste that rule set, and then include like the C code. So this one is the in-place add function, and let's just drop it at the bottom of the prompt. So I'm asking this reasoning model to read my rule set and to think about why one of those rules has not been met, and then like what it can do to come up with it. I probably should have put that code in a block. But what is interesting with these models is that unlike like GPT-4o, something like that, a reasoning model has been told to think through a problem and then like recursively look into different branches of its reasoning. So it will then come up with an answer and explain how it got to that answer. So instead of just sort of blindly giving you an answer and saying, hey, this is the result, it actually says, like, this is how I thought about it, and this is how I came to the conclusion. So it said, this code appears to be part of a arithmetic implementation. Good guess. Specifically an addition function. I mean, you could probably just guess that because it's called add. It's got 2 loops. It can read C code. Well done. There's 2 input arrays, X and Y, and the second one propagates any remaining carry onto the remaining digits in X. Okay, it says, after analyzing the code, it seems that the loop can be vectorized. However, there are a few potential issues that might prevent the loop vectorizer from vectorizing the code. 1, there are some conditional assertions, which actually, like these assertions, is talking about those probably. They don't matter that much because if you compile like release Python, then it doesn't compile assertions into the code anyway. Like no C compiler will do that. So it said, okay, these assertions might be considered as conditional statements that might affect the vectorization process. That's a good point. I like that argument. The second issue is that the second loop propagates to carry in the remaining digits in X. This has a conditional statement carry and I is less than m, that might prevent vectorization. However, this loop can be rewritten to avoid the conditional statement. To improve the vectorizability, that's a hard word to say, you can consider the following suggestions. Remove the assertions. I mean, you don't, if I just compile for release, it does that anyway. Or simplify the carry propagation loop. Instead of a conditional statement, you can use a mask to propagate the carry. This can be achieved using a loop that does this. So let's, if you just compare that answer to what I got from like GPT-4, and they're different types of models, and I'm comparing apples and oranges here because I should be comparing it with O1. But because I did so much testing on O1 yesterday, I'm in the sin bin, so I have to wait to get some more credits back on my O1. So I would show you, but it would probably give me a similar kind of answer. There's nothing, that's O1 as well, which is like the 300 something billion parameter model. This is using Llama 3.3 instruct, which is 70 billion. So this is like a reduced model. But its suggestion is, its logic and its reasoning here is pretty sound. Now, when I did this yesterday, it came up with a completely different answer. And this is what's interesting about this. So this time it said, here's an example of how you can modify the carry propagation loop to improve vectorizability. So I think it's talking about the second loop. So it's suggesting I change the second loop. So I don't know, Yola, let's do it. Let's see what happens. Okay. I think with time it, let me just benchmark time it before we do this. It's such a small cycle though. You're going to get a lot of noise in this benchmark, but we'll just see what happens. So let's just put a suggestion in there and let's see if it works. Let's also add the pragma statement. By now it should know what I want to do. Okay, so let's add the pragma statement in to say I really want this loop to be vectorized. Thank you very much. And see what it says. Just going to go through the comments because, okay, that loop was not vectorized. So it didn't work. But it was roughly the same speed, I think. And then if we go and run the unit tests, they pass. So the logic is fine. If we run the full math unit test suite, then the logic is fine. So it's kind of worked. Like the code is the same. The results are no faster. So that's kind of interesting. It's kind of tried to solve the problem, but not entirely succeeded. I think if you gave this some easier code, or you gave it a lot more code, it would probably be a bit more creative with its reasoning. But the reason I like this is because it's kind of come up with a cool suggestion. When I mentioned that this model came up with a different answer yesterday. And yesterday, let me zoom out, I'll show you, because it's pretty funny. This was R1's answer. This was, I think I put it in here somewhere. Where did I put it? Yeah, that was the $7 billion model. 7 billion parameters, not dollars. Apparently it costs 5 million. I still don't believe that. Where was it? Oh, this one, okay. this is the first one that Llama came back with. These are actually specialized instructions. This is a really interesting answer. What it's suggested in this one is that instead of trying to vectorize the first loop, you actually just you deal with them in batches of 4, and you use like specialized 128-bit instructions to do the same arithmetic inside the loop. Now, that is similar to what there was like this Llama post that went viral, and the developer asked R1 to basically like do stuff like this, and it did a pretty decent job of it. But he kind of gave like a before and after. He said like, this is what the code looked like before, this is what it should look like after. Can you apply that same pattern over and over again to the code? So that was the whole prompt. The prompt was like the code example. So what I'm doing here is a bit different. I'm just saying like, here's my rules, here's the code, you go and figure it out. And so that's kind of different. When I copied and pasted this code into CPython, I noticed that it made a mistake, which is that there's like an operation that it just completely missed. And so like the math is just wrong. So if you just blindly copied and pasted this in, it's wrong. That's like issue number 1 with this output, is that it just is not the same code, and CPython will just not multiply numbers correctly, which is a problem. When I told it that it had made a mistake, it then said, oh yeah, of course I did. And then it changed the arithmetic slightly so that it added this like missing shift, and then it came back with another answer. The problem with this answer is that it's assuming that so you've got 2 numbers here, x and y, and when you go into this, so the length of x is m and the length of y is n, and this function is only called when m is longer than n. So basically what the first loop should be doing in the code, like in the normal code, is it goes from the, like let's just kind of write this out. So if that's the first number and that's the second number, and it just did it in base 10, the first loop would do like that far, so like up to the length of the second number. And then the second loop deals with like the leftover, the carry from the first addition, and the rest of the numbers. So like that's how it splits it up. What this code is assuming is that the length of the second number is a factor of 4, because it's stepping by 4 each time and it's putting them all into 128-bit numbers. Why does that matter? It matters because if it is not a factor of 4, it will write, this is just a pointer, it's just, you're just writing back in place into the number, it will write into someone else's memory. So it's not immediately obvious just looking at the code, but that code is bad. So it will just write into something else's memory. So I just copied and pasted it in, compiled it, and just said, here you go, Python, like run your test suite. And it came up with a sort of like a kind of like a buffer overflow error. When you run Python in debug mode, it gives you like pretty versions of that. But it was pretty funny. Like it just kind of created this like horrible sort of memory problem. I then went back to Llama and said, oh, by the way, you made a buffer overflow error in that code. Can you fix it for me? It didn't really understand why it made that error. And then it just kind of produced like an even more complicated version of the same function with the same buffer overflow issue. So like in conclusion, it's like, this is what it did yesterday. This is what it did today. You can't just like, I wouldn't put all this in a script and go, here's like a 10 million line code base, go and make it faster, and then just like compile that stuff and ship it, because it's going to do stuff like this. Like it's going to do things like create buffer overflow issues, or just like the actual algorithm and the arithmetic it's doing is just different to what I asked for. So it's like so close, but it's not quite there. So that was like yesterday's YOLO. Yeah, I've seen people who are already, man, there was like a whole bunch of GitHub issues that were doing the rounds last week. Somebody made an AI that would go and like look at people's issues on GitHub and then like try and automatically generate a pull request and submit that pull request into the project. And it's like, okay, maybe that might work like 1 in 1,000 times, but it's then on the maintainer of that open source project to like read the code and see like, is this useful? Is it going to work? Do we have tests that cover that? So anyway, this is interesting, but I want to talk about R1 because that's what everybody's talking about. So I gave the same instructions to 3 different flavors of the R1 model. So there is now on GitHub Models, we added this yesterday, you can get the full 371 billion parameter R1 model, and you can give it instructions. Those suggestions, I would not ask R1 those questions. And this is kind of tripping people up yesterday. Like they were asking it kind of questions you'd ask like ChatGPT, and it's not that type of model. It is a model like the one we've just been talking about, where you give it a really long list of rules and a hard problem to solve, and it will think about the problem and try and come up with a solution. So like that's what you're supposed to use it for. If you try and use it like a ChatGPT, I don't know, you're not going to have a very good experience, and it's going to give you all sorts of silly answers. So yeah, don't do that. So I gave it the same instructions, and I saved some of the answers. Okay, I asked my laptop could only on Llama, so I can run it like on my laptop, which is like 4 years old. I can run the 8 billion parameter model. And that's really cool because this is like an old laptop. It's not particularly impressive. It doesn't have a really fancy GPU. And I can run a complex reasoning model on this old laptop. The problem was it got stuck in this, these reasoning models sometimes get stuck in this like recursive loop where it questions itself and then it just goes around and around in circles. So that's what happened with the $7 billion parameter model. I tried the 8 one, and that kind of came up with a suggestion, but it didn't really make any sense. One of my colleagues had access to the 14 billion parameter model, and this is what it said. So let me just show you this as text. And I'm going to recompile Python because it's interesting. I'm going to recompile it in debug mode and not release mode. And there's a reason for that I'll get to in a minute. So it gives you these think blocks, which shows you kind of like what its thought process is. And it said, I'm trying to figure out why the Clang compiler isn't vectorizing this loop. Let me look at it. It takes 4 parameters. It returns a digit. The goal seems to be adding 2 arrays of digits with possible carryover. Looking at the code, there are 2 loops. The first one runs from I0 to I less than n, which is the length of the array y. In this loop, they then add xi and iy, and I handle the carry after that as a second loop that continues processing the carry for the remaining elements. Okay, so it's figured out what the code does. I mean, this function is only like, I don't know, 15 lines, so that's a good first step. Now I remember, only because I've told it, but that there requires the loop to have a predictable number of iterations without any changes once entered. Actually, some of the other models stumbled on this one. In my instructions, I was pretty explicit. I said one of the rules with vectorization is that it needs to know the number of loops at entry, not at compile time. If it has at compile time, brilliant, but that's so rarely the case. Like modern vectorization algorithms just need it at entry time. Some of the other models were like, oh, it needs it at compile time because it's just using information from its training set and not the information that I gave it. So it's kind of skipping over the actual instructions and just kind of going with what it knows. And the control flow should be simple. There should only be one exit. And in the first loop, okay, so it's kind of figured out. Clang probably can't vectorize this because the second loop's iteration count isn't known at compile time. that is true. Vectorization relies on knowing how many times the loop will run so that it can batch process multiple iterations in the SIMD instructions. That's correct. And if the number of iterations is variable and unknown, especially dependent on data-dependent conditions like carry, the compiler can't safely vectorize. That is correct. Another point is the control flow. The first loop has a simple exit, but the second loop introduces a condition that depends on carry, which complicates things. This might make it hard for the vectorizer to predict how many iterations there will be. So the main issue is the variable trip count in the second loop due to the carry dependency. To fix this, maybe we can merge both loops into a single one that runs up to m, handling all cases without relying on carry for the iteration count beyond what's known at compile time. Okay, so what R1, this is the 14 billion parameter model. So we were just testing Llama 3370. So this is a much smaller model, not running on like specialized hardware. This is running on like my colleague's laptop, and it's come back with, here's why it can't be vectorized, and its reasoning is sound. And why don't you do it a different way? And I like this because it's, instead of just blindly doing what I told it to do, which is come up with like a vectorization solution, it's come back and said, like, here's my step-by-step explanation. It uses these think blocks. If you've not used the reasoning models yet, you basically get them and you can hide the thinking part, because sometimes it can be really, really long, so you might want to hide it. And then it kind of comes up with its answer. So it said, okay, here's my analysis. These are the rules that are violated. And my proposed solution is to merge both loops into a single loop that runs from I to M, handle addition and carry for all n elements, including the SB on n. So it came up with this answer. This answer does not look like the other answers, which is why I found this fascinating. So what it's done is it merged it into a single loop, and it said, like, I think this is a more efficient way of doing it. Now, whilst I've been talking, we've got a debug version ready to go, I think. I just have to clean it and rebuild it. If anyone has any questions, by the way, I can see the chat on my other screen. This is my dog doorbell downstairs. All right, so we're going to recompile that, and then we can run a little benchmark. That takes a while. It's annoying. Okay, so it's explained its changes: single loop, conditional check, and predictable iterations. So in the new version, it goes from I to M, but I is 0, so that's always known by the compiler, and M is known at entry time. So it should be able to vectorize that loop, but there are probably conditions why it can't. So yeah, it's just interesting. We'll see what it does in a minute. I really need a faster computer at some point. So again, so that was running on Llama, and we released DeepSeek R1 in GitHub models. The rate limit tier is high, so you can pretty much ask it like 1 or 2 questions like per day, and that's it. So that's why I said I don't recommend asking it what are some famous works of Shakespeare. Just ask anybody else. It's a waste of tokens to do that. Yeah, Taming of the Shrew, I don't know, Othello, there's some answers for you. So that was 14B, and I asked the same question to the full model, and we can look at that one. Where will I put it? Okay, here we go. All right, this is the full model, and this is sort of partial answer. GitHub models, you can use this playground interface, which is kind of cool. I also got, that's not great. Okay, there is another thing called the LLM CLI. I don't know if you've seen this. It is written by Simon Willison. It's like a little command line app where you can like send information to LLMs and it gets the answers back. And it's got plugins for it, which is really cool. LLM, I wrote a plugin for GitHub Models, so you can install the GitHub Models plugin. If you install that plugin, any of these models that you see like here, you can just give it the name of that model and your input, and from the command line, it will basically just use GitHub's API to like fill in the blanks. Like, so I can, what I did yesterday with this full answer is I just basically piped my prompt into the LLM CLI and said LLM-M. Okay, it's giving me a list of the models I can pick from. So like if I did, I think I did it earlier. If I just do LLM prompt and then pick the model like GPT-4o, and just ask it a question, like it will just use GitHub models to interact. It's free as well. You get free, a whole bunch of free tokens on most of these models. Some of them are pretty strongly rate limited, like O1 and R1. So you can only ask it a handful of questions, but it will give you back the answer directly from GitHub models, which is cool. So I can do GitHub/DeepSeek R1, and then I can pipe in or just ask it like to solve a problem. And that's what I did with the full model. And the full model, I think I got half the way through, but it really thought through the answer. And that's the difference between the 14B and like the full model, is that it went into a much like deeper thought process and actually thought about like each rule, whether or not it possibly was violated and for what reasons. You'll also see it kind of questions itself a lot. So it will say wait and alternatively but no, like it does that a lot with both Quen and this model. So you'll see it's like goes a really long thought process, and then I think eventually I just ran out of tokens. So it kind of got there. It was going in the right general direction, but I think I ran out of tokens, and probably by today or tomorrow we're going to get more, because there's been so much demand. So it's like that's been a bit of a limiting factor. Has it compiled yet? Come on. Okay, now this answer, what I found interesting about this one is that if I bring up Hopper, okay. If I bring up a disassembler, it's easier to see what it's done. This is probably dangerous though, because it's actually compiling it in the background. Yeah, someone in the comments said they were using Claude to write code and it took us a few turns to tell it what it got wrong. Yeah, and it's typically like unspecified assumptions. So it's assumed things based on other code it's seen that wasn't necessarily true in your code. And yeah, completely agree. It's not ready to replace us anytime, not yet, not anytime soon, in my opinion. Okay, so I'm sure not. you didn't come to the stream to look at assembly. So if we look at that as a block, then that was the loop. And so we can kind of put that to one side. That's the one it did, and the test I did was a bigger number. Oh yeah, actually, we should probably just test it. It actually works. Yep, so it's arithmetic, makes sense, which is cool. And let's just do a benchmark. That number's not big enough. The one I had on my screen was that, which is, let's have a look, R10, and N is 100. Okay. That's a big calculation. So like the bigger the calculation, the more you should see the difference, and the less noise you get in the benchmark. I'm also running OBS and a live stream in the background, so this is not the best place to do a benchmark. I can tell you the answer because I tested this yesterday. R1 suggestion is 10% faster, but there's a caveat. So I found this fascinating because it didn't make any sense to me. And I didn't understand why it would be faster, because it is essentially the same instructions, but the control flow, because it's one loop and it's fewer branches and the control flow is simpler. Therefore, it has fewer jumps to do in the instructions. So when I benchmark the R1 answer, doing that calculation, 2 to the power of 1, 2, 3, 4, 5, 6, 7, was 10% faster with R1's implementation of that function than the current CPython answer. And when I looked at this thing, which is the control flow graph, which is how the CPU actually executes the instructions, the graph is simpler, and there are simpler branches, and also the branching makes kind of more logical sense, which is awesome. And that's super exciting that it could make this 10% faster. However, its logic is sound, the math makes sense, but the sort of, that's the final thing, is that I compiled CPython in debug mode, and in debug mode, Clang isn't really doing any optimizations, and so what it's done here is just a literal translation of the C code into assembly with the blocks and the branches. If I then recompiled CPython in release mode and asked Clang to optimize it, it actually inlines this function anyway into the one that calls it, and it moves it changes the control flow and optimizes the control flow anyway. So the suggestion that R1 was making, Clang would have made that optimization anyway. So it's a really cool idea. I like what it was thinking. It was it is faster, but Clang would have made the optimization at the final hurdle anyway. So I guess in conclusion, I think this has got a lot of potential. I don't think this is the only model that's going to be able to do things like this. I thought that the Llama answer was pretty interesting. Not the one with the buffer overflow issue, but the one of the Llama answers was kind of interesting. What I think is potentially where we could get to with these models is you could have a specialized instruction inside of here, and this is what I want to play with next week, what I want to do is basically get the information out of the compiler on what it has and hasn't optimized, and then give that to the model as another input. Because at the moment, it's just looking at this code and it's just kind of guessing what Clang will do with the code. And it doesn't know because I haven't told it. I haven't given it that information. And that's why I brought up Hopper, because like that's what it looks like in debug mode. If I recompile Python, actually, if I just load like full Python, if I disassemble full Python, this function doesn't even exist. So like that's the kind of the challenge, is that to optimize this properly, you actually want to use Clang's output as a feedback into the optimization. I'm just trying to do too many things on my machine now. So maybe it's good for optimizing interpreted languages. That's one of the points in the chat. I absolutely think it could be. I think you would need to give it a long list of rules. And I think that's the key to, like, hopefully if you come out with anything from this live stream, is that like what you would do with these models is not ask it for some famous works of Shakespeare or other small questions. Don't treat it like a chat GPT. You should be giving it long lists of rules and hard problems to solve. And then the answer that it comes back with, read its reasoning, read its thinking and thought process, and try and understand what it's suggesting and why, and then just test it and see if it makes sense. Like sometimes it gets it wrong. Like we looked at that one where like the arithmetic was just wrong, or just like it gave a buffer overflow answer. But if you can give it rules like this, then potentially it could give you an interesting output. Another test I was playing with is that like Astral rough rule base. So like interpreted languages like Python, what could we do with that? And I thought like rough as a linter can do like these formatting expressions and stuff like that. You've also got inside rough, you've got like all these different rules and stuff like that. I thought maybe you could extract some of these rules and put them in as a set of instructions and say, like, these are the conditions that you need to meet, and I want you to produce better code. And that's measured by like the complexity of it, or the like the size of it, or like refactor. So not just like simple template like refactoring, because that you can do that programmatically, but actually try and get it to explore and think about all the different conditions for the rules. So what I did with this rule set, you could do something with Python as well, maybe like by using like a big linter rule set and then just like turning that into a set of instructions, giving it some code and saying like, how could you make this better or more efficient? And I think it would come up with something interesting. So what I want to do next is to like programmatically get the output from Clang on what it did and didn't optimize, and then actually use that as part of the prompt to say like, when it gives an answer, actually to get the output from Clang and say, okay, that was a nice idea, but Clang said this, and then get it to go back again to what it was thinking, and then see if it can do it differently. It might work. We'll see. But yeah, it's pretty cool. I'm super excited about this, and yeah, I'll post a written version of this at some point pretty soon. So yeah, any questions or anything, just ping me on socials, and I'll see if I can get back to you. Cool. All right. Thanks everybody. Thanks very much. See ya.